So over here, we'll be talking about the reactions of alkanes with halogen chlorine gas, which is a pale yellowish green gas, and this occurs when you have a mixture of alkanes and chlorine under the presence of UV light, ultraviolet ray. So we can use UV or Hμ to denote this. Now in this reaction, it is a radical mechanism, so we cannot control the extent of the reaction. So you have a sequential reactions that's ongoing. What happens is the chlorine will become free radicals that's reactive and grab the hydrogen and first form a monochlorinated CH3Cl, your chloromethane, and then subsequently this get attacked by more chlorine and get substituted, taking out a hydrogen, and on and on and on, resulting in a mixture of products. Now in the alkane series, it shows a regular increase in both the boiling point and the melting point as the molecular weight increases, and the reason is very simple, because when you have a higher molecular weight, you have more atoms, which means the size of electron cloud becomes bigger, which means that it becomes more polarizable. Suppose you have a pizza, right? The guy will just press on the pizza dough and then spin it and then it spread around. It's more polarizable, and hence you have stronger intermolecular forces of attraction, in particular the van der Waals forces. So when you have these dispersion forces, induced dipole, instantaneous dipole, is caused by the larger presence of electron cloud. So you have more energy that's required to overcome this stronger IMF. Now for stereochemistry, this branch of chemistry is super important, in particular in this module, right? You cannot get away from here. So this revolves about the three-dimensional aspect of molecules. Stereochemistry, the word stereo, stereophonic, all your speakers have surround sound, your Dolby sound when you're watching movies. So as a biologist and even chemists, you need to know the biological behavior of the molecules in 3D, right? When a model walks on the runway, did the judge or the audience only look at the front view? No. The model got to turn 3D. You see, it's about the posture, about how elegant they look. The 3D visualization matters. So in chemistry, we know that these sigma covalent bonds between the atoms are able to be rotated. You see the carbon-carbon bonds in an open chain molecule. So it will open, you can see from model here, right? Freely movement, rotating, okay? And if you look at these two structures, they are slightly different. So a new term here called conformation. And the first thing you need to know is conformations can refer to the same molecule but different posture. Think of it like a posture. Like for me, I have my body. My posture now is I'm putting my hands together. Not praying, just putting my hands together. Or I can put my fingers around my eyes. Or I can cross my arms. So these are my posture, my conformation. But it is not permanent. It is not always the case. What's permanent is my right arm is always attached to me, my body, my left arm to my body. Okay, so these are not conformation. Conformation is what I do with my hands, my legs. The first thing you have to know is your sawhorse representation of drawing it. So sawhorse representation views the molecule from an oblique angle. Oblique angle, now I'm trying to use this toy here, the model that I'm serenading, right, at an angle. So now you're not seeing an angle because you see straight through the bond, right? So if I turn it, can you see? Are you seeing through the angle? Yes, you are seeing through the angle, right? So you see the bonds here between the carbon-carbon, and you can see the CH bonds or CX bonds around there at the oblique angle, okay? The second one is the Newman projection. Right now, you're looking through the carbon-carbon bonds. In this molecule here, you see two black balls. So these are carbon atoms. So what you do is you look through. Can you see that? You're looking through the carbon bond, right? Exactly what you see in this drawing here, right? So of course you have the front carbon and the back carbon. The front one, you see that these three bonds here, the three lines must be at the front, and you have a circle that says that you are doing a Newman projection, and the three hydrogens behind belongs to the attachment to the back carbon. So give you some practice, you can watch the Lightboard video to learn a bit better. Now the stability of the conformations. You can, by default, look at yourself, some kind of posture. if I'm going to put my hand this way, okay, for 24 hours, my hands will feel tired because it's not my natural position. Compared to folding my arms this way is a bit better. So molecules are the same thing. You treat them as live, you know. I think of molecules chemistry as relating to us. So for a molecule like this, we have something called the staggered conformation, which means it's in, out, in, out, in, out. You see, alternating. So they are having more space, not bouncing each other. But if I turn it around here, just by 60 degrees, what do you see here? It is eclipse. Eclipse means the balls here are blocking each other. We have less space to maneuver around the region. So just like in a vehicle, you sit in a car, right? You're trying to squeeze 4 at the back row. Normally it can only accommodate 3 adults, but somehow you can squeeze 4. What do? You sit in, out, in, out. That's better staggered. Suppose this 4-person just put their bums at the back at the sofa, you see, it's too squashy, it's uncomfortable. So we know that in general, that the eclipse must be of a less stable conformer than the staggered conformer. And less stable means higher energy, right? More stable means lower energy. That's more preferred. We like to be low energy. Okay, high energy is very restless. So what affects the instability of the high energy eclipse conformer? Now you see that when you have eclipse conformation, the bonds here are overlapping with each other. So this is what we call the torsional strain. You know, torsion. So the interaction of the CH bond here by the anti-bonding orbital that's invisible here at the back, it will cause it to interact unfavorably, and hence you have an imposed eclipsing strain. So since we have 3 eclipsing bonds here, and each of them, the CH interacting negatively at 4 kilojoules per mole, so 3 times of 4 will give you 12 kilojoules per mole. Now the conformation of ethane, it is a cylindrical cycle. What it means is, right, if I try to rotate the bond bit by bit and you see this pseudo GIF, right, there will be a certain point of time where it is at staggered, which means low energy, and then as I rotate, it progressively becomes eclipse, high energy, and rotate again becomes staggered, and rotate again become eclipse, and rotate again become staggered, and rotate again become eclipse. So you see it's a cycle because molecules will have energy unless it is at 0 Kelvin, which means only potential energy and, you know, just vibrating very little. But all the bonds here are rotating because they have energy, movement of the bonds. So you see in this chart we are relating the energy minima and the maxima comparing to its conformers. Now for propane, the torsional barrier is 14 kilojoules per mole. I'll explain to you why. Over here for propane we have an extra carbon compared to ethane. That means we have a larger electron cloud of methyl group that could interact and bounce off the other hydrogen at the back more negatively compared to this hydrogen-hydrogen bond. You see, if you have 2 hydrogens here, right, they are rather small. They still interact negatively, but small repulsion. But if my fist right now is the methyl group, you see I put my fist here, what happens is I'm knocking this orange ball so easily. You see that? If I rotate the other bond here, you see, it's going to hit the other hydrogen atom so easily compared to before, which is only a hydrogen that doesn't go so near. So I hope you understand that when we have a bigger group here, it will interact less favorably.